Okay, here we go. I'm pretty sure that I have figured out how to stop the 5 minute limit. My apologies, I got rudely cut off on the last one. So I was talking about the fuse, and I just said that when I'm making basic electrical drawings, I would use that fuse symbol as just as a generic, essentially as a generic symbol for any sort of circuit protection. If you threw that down as just to say there is some sort of circuit protection here, whether it's circuit breaker, fuse, whatever, you would use something like that usually. Okay, we have symbols here for coils. When we're talking about coils, we're talking about the coil in a contactor. So when we power the coil on, it magnetizes, it closes a switch or series of switches. We will talk more about contactors at some point, no doubt, hopefully at some stage. If we ever manage to get back into a classroom together, we will do some sort of practical where we use contactors. But for the purposes of what we're talking about today, what we need to know is that a contactor has a coil, or a contactor or a relay has a coil and switched contacts, which are switched by the coil, and these are various ways of drawing that coil, the top one there being probably a generic one. And then the remainder of the contactor would be drawn with these symbols here. So we would have, if I go back one slide, the coil at the top here, and that would be drawn next to your switches or contacts, either single, double pole or triple pole. And we have, for each of those, we have at the top a normally open, a normally closed, a circuit breaker, isolator or on-load isolator. We have some more drawings here of lamps and so forth. These ones we would generally use on, these are the sorts of symbols we're using in house plans. So all of the previous symbols we're using if we're drawing circuit diagrams. So I'm drawing a picture of a diagram that I want someone to build. These drawings here now we're using if we have a house plan and I want to draw a picture for you or anyone and say this is the house, here are where the power points are, here are where the switches are, so on and so forth. So at the top there we have some lights, and we would generally use the different symbols. Earlier I said for lamps we would just use one generic symbol. If we were using a circuit diagram that would be the case. In this case we're looking at drawing a house plan, and so we would use the different symbols for the different types of luminaires, because we do need to specify that. If I'm drawing a plan for you to go and wire up a house, you need to know, well, what sort of lamps are you putting in. To be honest, I mean, I'm going to include more detail, right? I'm not just going to draw the fluorescent luminaire, for example, in the garage and then say nothing else. I would tell you or give a list of instructions or a list of equipment that you're going to need and what types and all that kind of stuff, because just writing a fluorescent probably doesn't tell us much information, but you would specify what types in the drawing. If we look a little bit further down here, then we have switches, and those are quite useful. So how we would draw a lighting circuit here is we would draw a picture like this with a switch, and that would be wherever that switch is going to be in the house, in the room that it's going to be, next to the door or whatever, and then I draw a dotted line that leads up to the lights that it's going to switch. If I have more than one light on the circuit, then I go dotted line, following my mouse by the way, dotted line, all the way up to the light, and then dotted line to the next light, and so on and so forth for however many lights are on that switch. If we have a two-pole switch, so a double switch, you would do the same thing, except you have a dotted line going off to one lighting circuit that's being switched by one switch, and another dotted line going to a second lighting circuit. Here we have two-way switching, so that's where we have two switches that switch the same lighting circuit, right? We know what two-way switching is, so our two-way switches will be drawn like this. I've gone too far. What have I done? Here we are. We have our symbol for socket outlet here. That's quite important. Again, this is something we would draw wherever we want a socket outlet in our house. We're going to draw this symbol here. And then we have the various other ones for different kinds of things. The general symbol for some sort of telecom outlet or non-power outlet, for example, a TV. You would use a similar symbol for your data connection, for RJ45 Ethernet plugs. Probably far more common than TV points these days, I suspect. What else do we have here? Electric buzzers, clocks, probably not used very often. General symbol for a motor, just a circle with an M in it. And often you'll see inside that circle as well, if you refer back to I think the very first slide in this slideshow, you'll see that we have the symbols for AC and DC. So often the motor will have that AC symbol, which is like a little sine wave drawn in there as well. We have that sine wave to indicate it's an AC motor. It looks like that is all of the pictures we're going to look at. So let's go into some of the terminology then. To activate and deactivate, so bringing into action and causing action to cease. So that might be something different to switching on and off. Sometimes we will activate something, activate a switch or activate a contactor to switch something off. So that's why we would use the terminology activate and deactivate. We have normally open contacts. I mentioned that earlier. So that if the contactor or relay is de-energized, as in it's in that switched off state, then the contacts are normally open. So this is a normal switch, right? The contact is open when the relay coil is switched off. But we can have a normally closed contact where if the relay coil is switched off, then the contacts are closed. So that may then be powering something when the coil is in the off position, and we actually switch the coil on to open the contacts and switch that off. Energized position, we're referring to the coil of our relay or contactor. So the coil will energize when we put power onto it. So then we would say that we would use that in conjunction with the above two terms, normally open and normally closed. So we would say that a contact is normally open when the coil is in the de-energized position or energized position or whatever. So we have their normal position, which is de-energized. And so when we draw contactors, we always draw it in the normal position. We always draw our contactor as if the power is off. So if the contact is normally closed when the power is off, then we would use a normally closed contact. If the contact is open when the power is off, then we use a normally open contactor symbol. Holding contacts, also known as maintaining contacts. Also, I would say we would use the terminology latching contact. So again, this won't make much sense until one day we actually get into a classroom and actually play with some contactors. But this is used to hold a contactor on when we use push buttons. If you recall in our practical rooms, not so much the emergency stop buttons, but the little push button switch on the side of the switchboard, that is activating a latching contactor or a latching contact on a contactor. So we don't have to stand there and hold that button in, and it's not held on. It's just a momentary press which activates a latching contact or holding contact to hold that contactor on. Overload contactors or overload contacts. So often on a contactor, particularly a large power contactor, we will have an overload built into that, which will switch off at a certain current. Operates in much the same way as a circuit breaker, but these are specific to the circuit that is switched by that contactor. Make contacts are contacts that close a circuit. Break contacts are contacts that open a control circuit. So an example of a break contact would be the emergency stop buttons in our practical room. So when we hit that button, that's breaking the contact to open the circuit for the contactor in the switchboard, and the contactor is what is providing power to all of our sockets. So when we push that emergency stop button, the brake contact in there opens the power to the contactor coil, the contactor switches off, and therefore all of the sockets in that room no longer have any power. Auxiliary contacts, we have those on contactors where you generally have three main contacts, three in a three-phase contactor, and then you may have additional contacts that you can use for whatever. The auxiliaries are often used as our holding contacts, for example. The main difference there would be our primary contacts or power contacts will be rated to usually a higher power output or higher current output than the auxiliary contacts. When we're talking about the rating of the contactor, we'd be talking about the rating of the power contacts, and then the auxiliaries may be a lower rating than that, and they'll just be used for switching or something. That's for something that's not going to switch a lot of power. Went too far. Interlock contacts are auxiliary contacts on a mechanically interlocked pair of contactors wired so that only one contactor can be operated at a time. Used to start delta and reversing contactor pairs. So this is where reversing is a good example, where we have a forward and reverse on a motor, and we would use a different contactor, one for forward and one for reverse. Now, without being able to show you or draw that picture, I can tell you that when you set up a forward and reverse circuit like that, if you somehow manage to switch both of those contactors on at the same time, you would end up shorting phase to neutral. So you have an interlock in there. We will definitely cover this when we get back to class, because there's just no way that I can do it from this angle, I'm afraid. But an interlock would give us the ability that one contactor is wired through the auxiliary contacts of the other, so we can never switch on one when the other is on. We can never switch them both on at the same time. So the power, generally power to the coil of contactor 2 would come through a normally closed contact on contactor 1. If we think about what a normally closed contactor is, or normally closed contact is, that means when my coil on contactor 1 is energized, the normally closed contact will be open. When my coil is de-energized, then that contact will close. So if coil 1 is energized and contactor 1 is on, that normally closed contact will open. If the power that's running to contactor 2 is going through that auxiliary, then I can't get power to that contactor. I can't switch on contactor 2 while contactor 1 is on, because it's going to be holding that auxiliary contact open. Once I've turned the contactor number 1 off, that normally closed contact, that normally closed auxiliary contact will then close again, and that will allow power to go through to the coil on contactor number 2. And it's a little bit more complicated than that, but that's the basics of how an interlock contact would work. The rest of the words on that page are fairly generic. Let me just give me a second here, team, and let me close that. I just want to have a look at how many slides we've got, because this is surprisingly difficult with no feedback, with none of you sitting in front of me and talking, and or even looking at me. It's actually quite hard to keep going. So 5-minute chunks might be not a bad idea. I will keep going for about half a dozen more slides, and then I'll take a short break and come back to you. Here we go. So we talk about electrical specification diagrams. As it says here, customers' requirements are set out as a specification. The specification usually consists of the following documents: site plan, schedule of electrical plant and fittings, and quantity schedule. I referred earlier when I was talking about the fluorescent light symbols on a wiring diagram for a house, or wiring plan for a house, that you'd have a schedule, or I said you'd have a list of what equipment you would need and so forth. So that's our schedule of electrical plant and quantity schedule. The site plan will be the drawing of the house with each thing labelled on it, and then these two here will tell us what those items are, and often where we're going to get them and how much they're going to cost if the quantity survey has done a good job. We will be doing hand drawing of electrical diagrams. That's in our practical books for this module. But it is worth being aware that in most cases somebody who's a full-time electrical draftsman, electrical engineer, something like that, is usually using CAD program. So it says computer assisted drafting here, but generally that would be the abbreviation would be computer assisted drawing. So we're making electrical plans and electrical diagrams on a computer, which is pretty standard, right? Day to day though, most Sparkies are probably still drawing most of their diagrams by hand because it's just easier. You could do that out in the field. They're not terribly complicated. You can convey ideas to other people pretty quickly. Obviously your familiarity at this point with any of the stuff that we're talking about will come almost solely from me standing at the board drawing these things, and just over time you're absorbing that information that when I've drawn switches or lights or contacts and stuff like that, you guys are picking that stuff up because I'm doing it all the time. So electrical drawing like that is still done primarily by hand. These are some of the different types of electrical diagrams. I would assume that we're going to go into a little bit more detail. Yeah, here we go. So a block diagram, simple block form to describe the general principle of operation of electrical installation. The diagrams only show the operational flow or sequence. Circuitry and component details are omitted. This is just to show somebody, for example, here is the transformer on the street. Here is the connection point to the house. Here is the meter box at the house. Here is the switchboard at the house. Just to show somebody this is how it's connected together. It doesn't tell you how many wires, what components, anything like that. This is a very simple sort of diagram just to show a layout basically. And this would have been something like what we'd done when we built our switchboards and circuits up in room 405 at the end of last year. A layout diagram like this, what you can see there is how you would, for example, lay out a meter box. So we've got a meter there, a recording ammeter, a voltmeter, ammeter, a circuit breaker. This is a basic drawing of what are the components going to be inside that box. Control circuit diagram or schematic diagram. This is sort of what we would what you'd be familiar with. It's random scribblings that I've put on the board, right? So usually we'd have two parallel lines, which one would be positive and negative, or phase and neutral, and then we draw our components in between them. We would draw circuit diagrams like this for drawing fairly complicated motor control circuits and so forth. I have got some projects for us to do that have some of these drawings that we need to interpret and wire up contactors and so forth. Once again, unfortunately we're not going to be doing any of that for the foreseeable future. And our power circuit diagram. So basically the power circuit diagram is the opposite of the previous one. So in the previous one we drew our control circuits, so that's where things get switched on and off, emergency stop buttons, start stop switches, all that kind of thing. The power circuit is going to show all of the stuff that's being controlled by those control circuits. So here we have a motor. At the bottom, as I said earlier, we've got we've got the M inside a circle to indicate motor. We've got the additional symbol with the little sine wave to indicate it's AC, and a 3 next to it, so that tells me this is a 3-phase AC motor. It's showing where the power is coming from, that we have a thermal overload, a contactor, and a circuit breaker, and then the supply coming from the switchboard. So this doesn't show any of the control circuits. It just shows us, doesn't show us, for example, this middle piece here, the contactor, where that contactor is being switched from. If we go to the previous slide, this here would tell us that relay coil there, for example, may be switching the contactor on the next page, and you might indicate that you'll draw something here. Usually a coil, you would have K, so you draw next to that like K1, and then over on this page, then you'd have next to the contactor, you would have K1. And so that would tell us, if we're looking at two different drawings on different pages, for example, that this control circuit on this page here has coil K1, and that's powering the contactor on this page here. So if I was building this, then I'd be able to tell, right, that's the control circuit for this contact. Single line and power system diagrams. A single line or power system diagram provides circuit information that is limited to essential details and characteristics of the system by depicting the way in which the equipment is interconnected. Yeah, I'm sure you guys can sit here and read that yourselves. Obviously, I'm skipping through these slides as fast as I'm reading them and as fast as I'm giving the information. But of course, you have access to these slideshows yourself, so you can go back and reread these anytime that you like. So you're just going to have to go at my pace for now. I won't read all the rest of this. But a single line or power system diagram is fairly similar to our block diagram. It's just where we throw components in there just to show how they're connected or what order they come in, without putting any complicated information about control circuits or anything like that. And there we have a single line and power system diagram example. Wiring diagram. This shares a lot in common with the control circuit diagram or schematic diagram that we talked about a couple of slides ago. And look at that. If you look really closely in here, you will see that we've got K on that contactor coil, and then over here it says K1 hold. So that's telling me that contact here is the holding contact for the coil K. As I said a couple of slides ago, generally we use K to when we talk about coils. I can't tell you why, to be honest, off the top of my head. I'm not sure why we label coils as K, but there you go. This is the wiring diagram is the one that you most commonly will come up against, and the one that you actually want, because this gives us all the information that we need. And you can see here that we've got the power side of things, overloads, fuses, motor, and then we've also got our control side of things here to tell me where things go, how they're wired together. If you bought a piece of equipment and you wanted to see how that worked, or you needed to fix it, you would be looking for a wiring diagram like this that would tell you where all the components are, what they're connected to, so on and so forth. Alright, location diagram. Now earlier when we were looking at the individual symbols, I said that we had the first few slides stuff that you would find on a wiring diagram, like this one here, and then the remaining ones I said would be if we were wiring up a house. That's how I would draw it, and this is what we've got here. So you can see that we have a room, and if you refer back to those previous slides with those drawings on them, you'll see that we have here, for example, a single switch it's connected to some sort of light. As I said, there's a dotted line there that indicates that that switch is powering this light. Same over here. Those would probably be wall sconces or something. And then we've got two-way switches. We see they've got the two legs on them, which indicates that they're two-way switches. And the dotted line going up to a light, dotted line going up to the same light, so two switches powering the same light. It's our two-way switching, and that looks like a fluorescent fitting to me. We've then got our sockets here, here, and here. That tells us they're the ones with the twos. That's a double socket outlet. This one here, three-phase socket outlet. This is how you would normally see a layout drawing for a house or location diagram, or any sort of building, I guess. Okay, I'm going to take a pause there. I will stop this video. I will upload it, go and have a coffee or something, and I'll come back and finish this one off. If you're still here and paying attention, well done. Thank you very much. Flick me a message or something and say, hey, I'm watching the videos and they're really good. I don't know. Okay. Thanks, team. I'll be back shortly.